Welcome to the deep dive. We're kicking off something really valuable for you today, our brand new CSWIP 3.1 exam prep series. If you're aiming to not just, pass that welding inspector exam, but truly get the material, you're definitely in the right place. Our goal isn't just memorizing answers. It's about digging into the why behind things, turning prep into real, usable insight.
That's exactly right. And to get that real understanding, we're going to break down actual multi-choice questions from the CSWIP 3.1 exam. It's a great way, I think, for you to pick up the knowledge quickly and properly, making sure you're not just test ready, but genuinely well-informed for the job. You'll see how these questions, even the tricky-sounding ones, often come down to core principles.
Yeah, I'm excited to get into it. I think this is going to be super helpful, give you a real edge. Let's just jump straight into the first set of questions.
Okay, sounds good. Let's start with a fundamental one about metallurgy. Question 1. It asks, when hypereutectoid steel is quenched at above its upper critical, the predominant structure will be A, austenite, B, martensite, C, trustite, D, sorbite.
Okay, wow. Hypereutectoid, quenched, upper critical. That sounds like a bit of a mouthful, doesn't it? Lots of specific terms there. What's actually going on?
It does sound complex, but let's unpack it. So first, hypereutectoid steel. That just means steel with a carbon content higher than about 0.77%. That extra carbon is key to how it reacts. Then quenching. That's simply rapid cooling. Think plunging hot metal into cold water or oil very fast.
Okay, rapid cooling. Got it. And upper critical.
Right, the upper critical temperature. That's the point where the steel structure fully transforms into this high temperature phase called austenite, which is option A, by the way.
Yeah.
Now, here's the crucial part. When you take that hypereutectoid steel, heat it above that upper critical temperature so it's fully austenite, and then quench it.
Rapidly cool it.
Exactly. The cooling is so fast that the carbon atoms, which are quite large, relatively speaking, don't have time to move out of the iron crystal structure. They get trapped. And this trapping forces the austenite to transform to something completely different. A very, very hard, needle-like structure, often quite brittle too. And that structure is called martensite.
Ah, so that's option B, martensite.
That's our answer, B.
Yeah.
It forms because there's just no time for the carbon to diffuse and form softer structures. If you cooled it more slowly, or if you took that martensite and gently reheated it, that's called tempering, then you get things like trustite or sorbite, options C and D. They're basically modified, less brittle forms. But the direct result of that fast quench from austenite, that's martensite.
Okay, so why is knowing that so important for a welding inspector?
Well, it's critical. Martensite is incredibly hard, yes, but it's also brittle. That makes it highly susceptible to cracking, especially things like hydrogen-induced cracking, which is a huge concern in welding. Think about it. Welding involves rapid heating and rapid cooling, right? So you can easily form martensite in the heat-affected zone right next to the weld.
Right, the HAZ.
Exactly. So if you see martensite forming or the potential for it, that's a big red flag for potential cracking. This knowledge helps you understand why procedures might call for preheating or controlled cooling rates or maybe post-weld heat treatment. It's all about managing that microstructure. You might need to check heat treatment charts, maybe do hardness tests, or look closely for cracks with NDT. It's about preventing failure by controlling the structure.
That's really clear. So the brittleness is the key takeaway for weld integrity. Makes sense. And speaking of preventing problems, the next question hits on preheating. Question 2. What does preheating for arc welding apply to? A, assembly welding only. B, assembly and tack welding. C, joints over 25 millimeter thick only. D, cruciform welds only. This one feels a bit more straightforward, but maybe there's a catch.
You know, there often is a detail that gets missed here. The main reason we preheat, as you probably know, is to slow down the cooling rate.
Right, slow cooling.
Yeah, and that slower cooling does a few really important things. It gives hydrogen more time to diffuse out, which drastically cuts the risk of hydrogen cracking. It also helps reduce residual stresses left over from welding and minimizes distortion. So multiple benefits.
Okay, but the question is what it applies to. Assembly welding seems obvious.
It is. But here's the often overlooked part. Tack welds. People sometimes think of tacks as just temporary little stitches, but tack welds are actually the first welds in the assembly. They experience the same thermal shock, the same cooling rates, the same stresses as the main welds. If a tack weld cracks because it cooled too quickly, because it wasn't preheated when it should have been well, you've just introduced a defect right at the start.
Ah, and that crack could then grow into the main weld later.
Precisely. It compromises the integrity from step 1. So tack welds need the exact same preheating consideration as the final assembly welds. They're foundational. Therefore, the answer has to be B, assembly and tack welding. Option A is wrong because it ignores tacks. C is too narrow. You might need preheat on thinner stuff too, depending on the material. And D is just oddly specific.
So the lesson for the inspector is check the preheat before the tack welds go into. Don't wait for the main weld.
Absolutely. Verify that temperature with temp sticks or pyrometers before any arc is struck, tacks included. It's about being proactive right from the beginning.
That's a great point. A small detail with potentially big consequences. Okay, moving on from process controls to material behavior itself. Question 3. A metal is said to have when it regains its original shape when stress acting upon it is removed. A, ductility, B, plasticity, C, malleability, D, elasticity. Yeah. So this is about how metals sort of bounce back.
Exactly. Bounce back is a good way to put it. This question is testing fundamental material properties, and the property where a material returns to its original size and shape after you remove the force that was deforming it. That's elasticity. Option D.
Elasticity, like a rubber band.
Perfect analogy. You stretch it, let go, it snaps back. That's elastic behavior. It's important to know how it differs from the others. Ductility, option A, that's about being able to be stretched out into a wire without breaking. Think copper wire. Malleability, C, is similar, but under compression, being hammered or rolled flat like gold leaf. And plasticity, B, is actually the opposite of elasticity. It's when the deformation is permanent. You bend a paperclip, it stays bent. That's plastic deformation.
Okay, so elasticity is temporary deformation, plasticity is permanent.
You got it. And for an inspector, understanding these is fundamental. Is this component designed to flex under load and return to shape, elastic?
Yeah.
Or will it permanently deform? Knowing these properties helps you assess if the material is suitable for the job, if the weld will behave as expected under stress, and if it meets the design requirements for safe operation. It dictates how it performs in the real world.
Makes sense. It's about predicting performance. Okay, let's switch to a specific process, submerged arc welding. Question 4 asks, what would you be most critical of if submerged arc welding is used to make butt welds? A, the root gap tolerance, B, the angle of preparation, C, the root face width, D, the gas cut finish.
SAW is a powerhouse, right? High deposition, deep penetration. But what's the key thing to watch out for in butt welds?
Right, SAW is known for those high currents and deep penetration. And because of that deep penetration, the most critical parameter, especially for butt welds, is actually A, the root gap tolerance.
The gap at the bottom of the joint. Why is that so critical for SAW specifically? Well, think about that high energy and deep penetration. If that root gap is even slightly too wide, you can easily get burned through the weld. Metal just falls right through the joint. Or you might lose the molten pool control, lose the protective flux covering. Basically, the process breaks down. On the other hand, if the gap is too small, that deep penetration might not actually reach the root. You'll get lack of root penetration, which is a serious flaw.
So it's a very fine line with also because of its power.
Exactly. It's much more sensitive to root gap variations compared to, say, the bevel angle or the root face width or even how clean the edge cut is, options B, C, and D. Those things matter, of course, but it's also it can often tolerate a bit more variation there. The root gap, though, that needs to be spot on. So for an inspector, meticulously checking that root gap before welding starts, maybe with a feeler gauge or a bridge cam gauge, is absolutely paramount for SAW butt welds. Get the setup wrong, and you're almost guaranteed a defect.
Okay, so precision in the setup, especially that root gap, is key for SAW. Good to know where to focus. All right, final question for this deep dive. This one's about testing. Question 5. A suitable mechanical test for a component for vibrational loading would be A, impact, B, tensile, C, compressive, D, fatigue. This is interesting. Testing for something that's constantly shaking or vibrating. How do we simulate that?
Yeah, this gets into real-world service conditions. Vibrational loading means the component is seeing repeated cycles of stress over and over again. And crucially, these stresses might be quite low, well below the level that would cause it to break in a single pull, like in a tensile test. But applying even small stresses repeatedly can eventually cause failure.
Through wear and tear, kind of.
Sort of, but it's a specific mechanism called fatigue. Fatigue is the weakening of material specifically because of these repeated cyclic loads. It causes tiny cracks to start, often at microscopic flaws, and then grow with each cycle until the component suddenly fails. So the test, designed specifically to simulate this kind of cyclic loading and measure a material's resistance to it, is fatigue testing.
Fatigue testing makes sense. How does that differ from the others then?
Well, an impact test, A, measures toughness resistance to a sudden sharp blow, like hitting it with a hammer. One big shock. A tensile test is a single steady pull to see how strong and ductile it is. A compressive test C is a single steady push. None of those simulate the repeated back and forth or up and down loading that causes fatigue failure over time.
So different tests for different failure modes. Impact for sudden shock, tensile compressive for steady loads, and fatigue for vibration or cyclic loads.
It's exactly. For anything that vibrates in service engine parts, bridges, aircraft components, understanding its fatigue life is critical for safety and reliability. A simple static test just won't tell you how long it will last under those dynamic conditions.
That really clarifies it. It's about matching the test to the real-world stress.
Yep.
Wow, okay. That was a fantastic run-through of those 5 questions.
Yeah.
We covered everything from steel microstructures like Martensite and why it's brittle, to the importance of preheating tack welds, not just assembly welds, the definition of elasticity, pinpointing root gap as the critical factor in saw butt welds, and finally, why fatigue testing is essential for vibrational loads. I really hope breaking these down helps you see that it's not about rote memorization. It's about understanding the underlying principles. Knowing why Martensite forms and why it's bad, why tack welds need preheat, why root gap is vital for sawability. That's the knowledge that makes you a truly effective inspector. That's really the whole point of this series. Making this stuff click, making it practical for you.
Absolutely.
Yeah.
And maybe just to leave you with something to think about. We talked about some critical details today. Tiny structural changes, small gaps having big impacts. So the thought I'd leave you with is, what other seemingly small details, maybe less obvious ones, could be just as critical in different welding processes? What are those other hidden sensitivities an inspector needs to develop an eye for? Keep thinking about those subtle things.
That's a great challenge. What else is lurking beneath the surface? Fantastic food for thought. Thank you so much for joining us on the deep dive today. We're really excited about this CSWIP 3.1 exam prep series. We'll be back with more deep dives soon. Until then, keep learning, keep asking questions, and keep digging deeper.